Okay, so here's an example question of how to do a buffer calculation involving the formation of a buffer through the partial neutralisation of a weak acid. So here's our question. We've got a certain volume and conc of acid, and it is reacted with a certain volume and conc of base, and we're asked to find the pH of the resulting solution. It's also given us the Ka of the acid there. So we should already know that carboxylic acids are weak, but even if we didn't, we can look at this Ka and see it's times 10 to the minus 5. That tells us that that's quite a weak acid. So how are we going to go about this? This method, by the way, isn't only applicable to buffers. If ever you've got any solution and you want to figure out what its pH is, this is how I'd start off this method. So it's the ice method, very similar to the one we would use when you did KC. So first of all, we're going to find out the initial moles of everything we start with. So I would just write it underneath the chemical in your balanced equation. So our initial moles of propanoic acid is CV, volume times concentration, so 0.025 times 1, which if my maths serves me correctly is 0.025. We can do the same for the sodium hydroxide, so that will be 0.03 times by 0.15. Again, I'm just doing volume times concentration, and that will equal 0.0045. We're not starting with any of our salt or any of our waters. Next, we can think about our change in moles, just like we would if it was a KC question like this. So, which is our limiting reagent? Which is going to run out first? Well, it's a 1-to-1 ratio, so they're going to get used up at the same rate, and I have way less moles of sodium hydroxide. So sodium hydroxide is going to run out first. I'm going to use up all of that, so that has changed, which I'm just going to keep track of on my arrow, by minus 0.0045. As it's a 1-to-1 ratio, that means my moles of propanoic acid must also change by 0.0045. Just to point out, these numbers won't always be the same. If this was a 1-to-2 ratio, then my moles of propanoic acid would change by this times 2. Right? If this was a 1-to-3 ratio, my moles of propanoic acid would change by this times by 3. So you do need to look at those big numbers, those molar ratios. And again, as it's a 1-to-1 ratio, my moles of salt will change. This will be positive 0.0045. Because if your moles of reactants are decreasing, then your moles of products must be increasing. So banging all that in a calculator, we know we're going to end up with this many moles of our salt, and 0.025 minus this number moles, 0.0205. We now have our equilibrium number of moles in our beaker, or whatever it is we're doing this in. So next we need to select the correct equation based on what we're dealing with. So if I just had a weak acid, I would use the weak acid equation. If I just ended up with some strong base, I would use the strong base equation. Now, what we've actually ended up with is some strong acid and some salt. But this salt can dissociate, can break apart to release your conjugate base. So what we actually have is a solution of weak acid and conjugate base, because this salt will fully dissociate. So we have a buffer. This is how you can form a buffer through the partial neutralisation of a weak acid. What we did is we took some weak acid and we neutralised some of it to get some base, and we left some of it as weak acid. So we have a buffer. So before we can bang this in the buffer equation, what we're going to do is change it into the concentration. Now, there is a little caveat here which I'm going to go through at the end of the video. But for now, we're going to change this into our conquered weak acid, moles over volume. Bang all that in a calculator and we'll get that. We can do the same for our conjugate base. Now, as each mole of salt contains 1 mole of conjugate base, and that's true because we have a 1+ metal, that means that my number of moles of salt will be equal to my moles of conjugate base. So I can say moles over volume of conjugate base will be like so. Be really careful here. You'll notice the volume I've used, because we're trying to find the pH of the final solution, you have to use your final volume. So I didn't just use 25 centimetres, I didn't use 30, because both of these have been added to the same beaker. If this was my acid and this was my base, both of these have been dumped into the final solution. So we need to talk about our final volume, which is both of the volumes added together. So bang all that in a calculator and you'll get this. We can then apply that to our buffer equation. So H plus equals KaHA over A minus. Stick all that in, feed all that in. We know the Ka from the question. We've got our moles there, and you will end up with 6.104 recurring times 10 to the minus 5. We can then say pH equals minus the log of H plus, so minus the log of this number here, and we will end up with 4.21. Apologies, there you go. With 4.21. Okay, so if you found that a little bit challenging, a little bit tricky, I would suggest stopping the video here for now, having a little bit of practice at those questions which are the next task, and coming back afterwards and just watching the last minute of this video. If you think that this is okay, I'm okay with this, I'm going to talk about one extra thing now. So stop the video, try the next questions if you found this a little bit challenging. If you didn't, let's carry on. So just one extra thing to point out here, in reality, we actually didn't need to divide by the volume here. So the reason we didn't need to do that is because here is our buffer equation. I'm just going to rewrite that so it looks a little bit less messy. And I'm just going to use HA over A minus, again, just to simplify it a bit. Okay, so what we had is the moles. Here's our moles, equilibrium moles, and we divided by the total volume. Remember, it has to be the total volume to get the concentration. However, if I think about this equation here, I can substitute the concentration of HA, because concentration equals moles over volume, I can substitute the concentration for the moles of HA over the total volume. And using that same equation again, I can substitute the concentration of A minus for the moles of A minus over the total volume. But if you actually look and you think about the maths of this, these volumes will cancel. So actually, what I could have done in my question is I technically could have missed this step out and just straight away stuck my equilibrium moles into the expression. I didn't technically need to divide by the volume. However, this square brackets does mean the concentration of, so if you found the concentration and put those in, that would give you exactly the same number.